So now that we've defined what an NFA is, or a non-deterministic finite automaton is, I want to define more formally what computation is on a non-deterministic finite automaton. Previously, we've seen a high-level view of how it works, and we talked previously about the concept of non-determinism and a couple different ways we could think about non-determinism. So let's give a formal definition. Formal definition of computing or computation. I'll say computing for a NFA. So just like with the DFAs, I can exactly define the computations of such a machine. So recall, NFA takes a state and input symbol and returns a set of states. Ooh, this marker's getting a little funky. Trying to get rid of this one. There we go. It's gone. So similar to a DFA, we define an extended transition function. Transition function delta hat that takes as input a state, which you'd presume is like the state for which you're currently at. So if you want to perform the computations of the NFA, you would put the start state and then whatever string you want to process. Input a state and a string of input symbols. A string of input symbols. But instead, it returns a set of states. So remember, that's one clear difference between the DFA and the NFA. Is remember, the two things that characterize it differently was the transition function. It gives you a set of states. That means the extended transition function also has to have this property. But remember, non-determinism is a generalization of determinism. So it's going to have it where it's capable of being in more than one state at once. So we're going to define it now formally as follows in an inductive way. You can also think of this recursively, of course. So we're going to define delta hat as follows. So here's our basis. So this is what you do if you have an empty string. So delta hat, given a state q and the empty string, similar to just how we had it with the DFA, it stays at that state. It just stays at the state. So you'll notice that this looks exactly the same as the DFA's definition of the basis. Just get rid of these curly braces here. Because remember, it's a set of states now, not just a state. So when no symbols are read, the NFA remains in state Q. So that's the first part. Now, the other part is the inductive part of the definition. This is easily the most interesting part of today's lesson, is how this works. How exactly does the transition operate such that you could transition to a set of states to another set of states, which we've never seen that concept up to this point. So given string W, and again, we're going to use the same kind of decomposition as we did before. We're going to use the same decomposition where we're going to imagine this is all the string except for the last symbol. This is the last symbol. Where A is the last symbol. And X is the string W less A. So compute delta hat Qx. So we're going to imagine we've computed this. Then follow any transition labeled A from this set of states. So it means that once you've computed this, in the transition diagram, you'll look at every one of those sets of states. And if you see a transition on A, you're going to follow with your finger on each one of those states and see where you end up being. So each of them one at a time, you'll just look at each one and see if it transitions on A to another state. If it does, and just tell me which set of states that it is in the result. So more formally, it means this. Formally, if delta hat Qx is equal to a set of states P1 containing states P1, P2, all the way up to Pk, where there's k states in here, what you would do is you would delta hat of Qw is going to be equal to the following. So remember, like I said, you're going to follow with your finger each of the transitions of the set of states on A. Some of them might die or get killed, quotation marks, but other ones may successfully find another set of states or just another state. So for each one of these, you would perform the transition function on that state given the symbol A, but you're going to do it over all of these. And you're going to put them all into the same bucket together without the duplicates. So you just go over all of these states, one after the other. You compute their transition function, and then you take the union of all of the states, the resulting states. So you just, like I said, for each one of those states, you're going to look at if there's a transition to another set of states. You're going to collect those up for each one of these states, put them all into the same bucket. That's a set of states. So the resulting set, that is what delta hat QW is. So this is how we could define computing for an NFA. So let's do an example. So for our first example, let's consider the string W is 0, 1, 1, 0, 1. So for our next example, we're going to be just considering the same string we had from when I showed you a high-level version of computing for this NFA. So I'm going to show you how we use this formal definition in this case. And then we'll see another string just to see how this works with different strings, because I want to go a little careful with this. Okay, so delta hat, so we're going to be building up to the string one symbol at a time. So we're going to start off with delta hat Q0 on the empty string. Well, what is that? What is that? Well, the basis was that it's Q0, right? because I haven't read anything. So it stays in this set of states. Now, let's consider when we read the first symbol, delta hat Q0, 0. So we're going to read the first symbol. Well, what does it mean? Well, we take each one of these states in here. I apply the transition function on whatever the symbol is. The symbol in question is the symbol I'm currently reading, right? So I read a 0, so it means that whatever delta hat of this would be was this, where I apply the transition function to each one of the symbols, no, not symbols. I apply to each one of the states in here. Sorry, I'm getting really excited here. I'm getting so excited that today is just a wild one. There's a lot on Dan's mind today. So anyways, I have, when I take the empty string, I end up with Q0. So what to define and compute, to compute on this symbol, I read 0. To do that, I'm going to now consider each state in this set. I'm going to apply the transition function. I'm going to apply union across all of these, okay? So here I just have 1, so it's really easy. So it's just Q0 on 0. So Q0 on 0, okay, it just says, I'm supposed to just stay in Q0. Nothing too interesting, right? Okay, we got delta hat of, now we're going to read the 1. So Q0, 0, 1. So next we have Q0. So remember, it's just one state here. So I just do the same thing, except now I'm going to try it with 1. Remember, that's the one we're considering here. So I have 1. So I have Q0, 1. So on 1, it stays in Q0, but it also goes to Q1 at the same time. So it's Q0, Q1. So now notice now I have 2 states. Let's compute delta hat Q0 of 0, 1, 1. So, because that's the next symbol we're reading. Well, what does this say? It says whatever the result of applying delta hat to 0, 1, I'm going to take each one of those states. I'm going to apply the transition function on the symbol 1. So this will be delta Q0, 1, union delta Q1, right? Because that's the other state. I go through each one of these and I applied the transition function with that symbol, that one I'm reading. Well, Q0 on 1. Q0 on 1 is just Q0, Q1, right? However, in Q1, if I read a 1, notice there's no transition out or in Q1 on symbol 1. So that one, it gets killed. Hence, that's nothing. It's an empty set. And that means that the result of the union operation here is just the states I'm left with are Q0, Q1. Let's consider the next symbol. Delta hat Q0, 0, 1, 1, 0. Okay, so that means I'm going to apply now the transition function to Q0 and then Q1 on symbol 0. Q0 on 0. Union delta Q1 on 0. Well, on 0, Q0, it stays in Q0, right? Upon reading 0. How about here? On 1, on Q1, reading a 0, it goes to Q2, right? But only Q2. So we end up with Q0, Q2. So now we have Q0, Q2. Let's read the last symbol. So 0, 1, 1, 0, 1. So now, over that set of states, I'm going to read 1. So Q0, 1. and whatever the result of the transition function for Q2 on reading 1. We're going to take these, lump them together, okay? So Q0, 1. So remember, it's a set of states. So if we have duplicates, we just discard them, right? Like, it doesn't matter. It's a set, not a multi-set. So on 1, Q0 gets Q0, Q1. Right? However, on Q2, when it reads a 1, it stays in Q2. So notice that the result will be Q0, Q1, Q2. So please note that Q2 is an accepting state or final state. So it accepts. Do you see that? And in fact, what I want you to do is, in our previous lesson, we've seen a high-level version of how this is being carried out. I want you to look at the result from each one of these as soon as I read the first symbol. Take a look at what the sets look like and read the columns of states. And you'll see that they match up exactly with these ones. Fascinating stuff, right? So there is no weird, funky business happening here. It's all just a bunch of union operations on transitions, where now we have sets of states, and the union operations take care of what happens when we have multiple states to deal with. So let's do another example. Let's consider when the string W is just 1, 1, 1. So it's just 3 ones. Let's consider this scenario. So let's go through the same process. I'm going to start off with the base case of the definition. Q0 on the empty string. Well, this should just be Q0, right? We haven't read anything. Now, let's read the first symbol. So on 1, we're going to apply the transition function. Q0 on 1. On 1, notice it can be Q0, Q1, right? Now, let's read the next symbol. So remember, I'm going to read now the 1 at the end of this string, because everything else has been computed. I have Q0, Q1, so I'm going to apply the transition function on each of these, take the result, and union each, okay? So I'm going to take the result of each and put them all together in one bucket. So I have Q0, 1, union delta Q1, 1. And naturally, what happens? Okay, in the first case, Q0, 1. We get Q0, 1 again. Union on a 1 in Q1. We get the empty set. There are no set of states other than the empty set of states in that case. So we end up with Q0, Q1. And now we have to read the last symbol. Delta hat, Q0, 1, 1, 1. So we're going to apply the transition function on Q0 and Q1 each. On a 1 again. So delta Q0, 1, union delta Q1, 1. This should look awfully familiar to you. And there's an actual really nice property that's happening here, by the way, with why we put this loop here at the beginning, the self loop. But notice here that, again, we'll get Q0, Q1, union, the empty set, which ends up being, again, Q0, Q1. Now I have a question for you. Does it accept or reject the string? Does it accept or does it reject? Accept or reject. Are any of these states the final state that in our NFA? Remember, we only have one. We have Q2. None of them are, right? None of these are. So none of the states are So there's none of these are in F. So in this case, we would reject, right? So again, there's going to be another example here in the notes. But now I want to define what the language of an NFA is. Because before we had a definition for the language of a DFA, now we would like to have a definition using our formal definition of computation. I'm getting really excited here. Of an NFA. So we got a language of an NFA. So given an NFA M, we're going to define the language of M, L of M, to be equal to all strings W such that delta hat Q0 on string W. So remember, this is defined for M. So what happened in our previous example? We looked at the set of states and we didn't see the final state upon reading the input string, right? So there seems to be something really important about having at least one of the states being in F. So whatever the result of this is, one of these has to belong to F. So one way I can write this out is I take the intersection with F, and if there's any ones in common between these two sets of states, then this resulting set will be what? Non-empty. It'll be non-empty. Meaning there's at least one state that's in common between these two sets. That's what the intersection would give me if it accepts. So any set of strings that follows this would be called the language of this NFA. So as long as when I'm done reading the string W with my NFA, if in the result has one of its states being in F, keep in mind it can be more than one, we would say that it accepts. Hence it belongs to this language. So just to kind of bring this all together, if we think about this in terms of the guessing process that we had when we talked about perfect guessing, is that the whole idea here is that if I give you a set of a string W, there exists a sequence of choices that leads to the final state. However, in that case, if it rejects, it means that there is no chain of guesses that will get me, or good guesses, that will get me to the final state. They're all just going to be bad guesses. So there's no way to accept W in that case. So this is the formal computational definition. This is our definition for computing for an NFA.